Let's see here. Think that's good. Let's make sure we can get on here as well. Okay. All right. It looks like we are good to go again. So we have what I have here to actually get started with. So once more, welcome back to another live stream where we are practicing the AP Calculus exam. One thing that we have to note here is that I reprinted the 2014 free response questions. And again, this is something that we've done before about a month ago, where I've only scored 43 out of 54. I think that was actually one of the lowest of the scores that I've done so far. So since we've gone over many other tests, we can go ahead and redo the 2014 one to make sure we are on the right track to be able to score properly here. Okay, and so I think with that, that should be a good moment for us to again continue practicing. And anything that, at least as an example for the students that do watch this sort of content, is that you can definitely go over the types of problems that you have missed and to make sure that we are on the right shape to move forward. Obviously, there is quite a bit of time, so I'm not here to memorize any answers, but is to make sure that we can go through all the steps properly since the last time that we went over this together. So as usual, again, all the questions will be printed out here, but we'll be copying them once more down on our reliable notebook so that we can follow along exactly how to go about this. And as before, the way that this test is situated is that the first two problems are done on the graphing calculator. So we'll have our TI-83 Plus, our very handy and reliable calculator, waiting for us here on the side as we go through these first problems. Okay, so as always, you can submit any of your questions to the email over on that left side. We're working on a couple right now, but the labcoatmath@gmail.com is a way that you can reach out for any specific help that you need, or anything that can be reached out to us directly through the chat. All right, I think we are just about good to go here. So let's go ahead and get started with question number 1. And with that, we should be able to have everything written out here as we begin on this test. So it says here that grass clippings are placed in a bin where they decompose. Okay. For the time frame going from 0 to t to 30, the amount of grass clippings remaining in the bin is modeled by A of t being equal to 6.687 multiplied by 0.931, all raised to the t power, where A of t is measured in pounds and t is in days. Okay, good. So we have that all listed up for us as the context of the problem. So going to part A, it's asking us to find the average rate of change of A of t over the interval from 0 to t to 30 days. Okay, and then include units in the answer. Okay. All right, so we have that all sorted out to begin with. So here we go. We have average rate of change, right? That is going to be the key word for us in order for us to then describe what we are looking at for this type of problem, right? So average change of A of t, that's going to be the very simple equation that is going to be called up here, again, with our interval from 0 to 30 days. Now, actually, that reminds me. Let me make sure we change all this to make sure we're doing this correctly. So this is 2014. Really quick here. Actually, kind of forgot about that since the last stream. There you go. Okay, so that's all up to date. So we should be good enough to get about this problem. So average rate of change across the two different time periods here means that we set up the equation of a of 30 subtracted by a of 0 all over 30 minus 0. Okay, so this equation can be very easily submitted through, again, this type of problem, which will be done through the calculator, right? Meaning that we get the 6.687 times 0.931, that raised to the 30 power, subtracted by the 6.687 multiplied by 0.931, all raised to the 0 power when we plug in, all over 30. Okay, so that's how we get started with that problem right there. So this is something that we'll be submitting straight away into our calculators here. So if we clear that out, we can begin here. That it's going to be all of the 6.687 multiplied by specifically 0.931 raised to the 30th power. Okay, so we close that off, and then we subtract it with the next portion here, so 6.687 multiplied by the 0.931 all raised to the 0 power, and then we close that off, and then for all of this now is going to divide it by 30. Okay, so again, a little bit of parentheses maneuvering here, but that is going to be required for us to be able to then make sure that we have everything in the numerator. So again, both the subtractions, the 6.687s on either side with the 30 exponent, making sure that they're only applied to the 0.931, all divided by the 30 there. So that gives the answer of negative 0.9197 if you round that properly. Okay, so this is negative 0.9197. Okay, now they did tell us that the units are going to be important for this problem, right? So because A of t, again, remember A of t is measured in pounds and the t is measured in days, the average rate of change will then end up with the units of pounds per days as a result, right? So that's going to be a decrease in the amount of grass in the bin during that time. That does make sense for us, as this is something that, again, the grass is decomposing, and so the amount of grass measured in there should be decreasing as well, with a negative on the average rate of change. Okay, moving forth to part B here, it's telling us that we need to find the value of A prime. So A prime of 15, and so using correct units, interpret the meaning of the value in the context of the problem. Okay, so we have this problem now asking us to find A prime of 15, which this can be done exactly in the calculator. Right, so as a note here, what we're going to do is that we can do the derivative function. So then we can just plug right in for the 6.687 multiplied by 0.931. I'll raise the t again. This is for t being equal to 15, right? This is going to go into the calculator as something that it can tell us immediately in the numerical value. So let's go ahead and put that right through here. So for me, it will be the math and 8 button, meaning the function derivative of what's going to go inside of there. So copying everything, 6.687 multiplied by all of 0.931, raised now to the t power, making sure that we leave it in the variable form because it's the function that's going to be derived here. So we close all that off on that part at least, and then we told it that this is now for the variable of t. That's the variable that is going to be derived, and for the value of 15. Okay, so by doing that, we do get the result of negative 1.64 as a result. Okay, so it's negative 1.64 Okay, so remember, because we took the derivative of a in respect to t, right? So again, this is the a of t function taking the derivative with respect to time. This means that it's going to be pounds per day as well in terms of the units. Okay, right? So what this means in terms of the problem though, right? So the value in context of the problem. So that negative 1.64 is then going to be, right? So we can note here that the negative 1.64 pounds per day is the rate at which the grass in the bin is being decreased per day. Right? Again, given that it is a negative value, the pounds of grass are being removed from the bin as the grass decomposes, as is explained in the start of the problem. All right, very good. Then for part C, it tells us that we need to find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval going from 0 to t to 30. All right, so we have our next problem set up right here. All right, so we need to find a specific time which the amount of grass clippings in the bin is equal to the average amount of grass over the interval 0 to 30. All right, average amount of grass, right? So that means that we're going to take the average value of the a of t function, right? Well, it should be capital A, right? That because a of t is the grass in the bin at any time. The average value of that will then be equal to, we have to set up the average value equation from going 30 minus 0 of the integral from 0 to 30, as those were the time intervals given that we want to take the average value of the a of t function, right? So this can be done in the calculator, right, as shown. Again, this is a definite integral, which during the calculate section we can easily find as we run this straight through our calculator. So again, this can be Math 9 button for the definite integral. So this will be for that a of t function, that the 6.687. So let's put that through. So 6.687 multiplied by all of the 0.931 raised to the t power, making sure we close that. Okay, leaving it in the variable form as we are taking the integral of variable t. But with it being a definite integral, we have to go through our limits of 0 to 30 for that example. Okay, so we get a result of 82, but something we have to keep in mind though is that because this is average value, we actually need to go back, almost made that mistake again, where again this may be multiplied by the 1 over 30 coefficient as we stated right there as part of the average value function. Right, this is very important to put in there. So by multiply by the 1 over 30 as shown at the very end right there, then from there we can get the average value of 2.753, right? 2.753. And because this is average value of the a of t again is measured in pounds, the units stay exactly the same in terms of pounds once more. Okay, so 2.3 pounds is the average, okay, that we need to keep in mind. But we still need to find the t in which this is going to be the case, right? So remember, we're looking for a of t such that it's equal to the 2.753. Again, we need to find that t, okay? If we want to do this on calculator, right, that means we need a graph, right? And on the other side, if we did a of t minus the 2.753, that's going to be equal to 0, and we can find the t once the a of t is equal to 0 once we calculate it as such, right? So this needs to be done on the graph, and then we can then find the t if we can find a 0 after moving that 2.753 over from the right side. So with that, we can open up our graph function right here, and we can start putting this in. So again, this is going to be all of the 6.687 multiplied by the 0.931 raised to the, remember we have to do the x value now because we're graphing on the xy plane. It will require us to make sure we do x in terms of the variable for that. And then we need to subtract it by 2.753 so that we can wait to see where the cross on the x-axis is going to be. Now, window-wise, I think it'd be very good for us to make sure we go from 1 to 31. Negative 2 to positive 2 on the y's are fine because we're just looking for a cross on the axis, but making sure our frame of our window for the x's are indeed correct. So we can run the graph and we can take a look. Right, there's indeed a cross right there, and it just continues to go down and down after the fact. Okay, so we can look for that. Right, we can go and trace for the 0, making sure we go to the left side of that graph. Okay, something above the x-axis, and then something below, making sure we see that negative on the y, such that we can get a specific value right there. So 12.413 looks like is going to be the case, and the y is equal to 0. Okay, so we get 12.413, and that's how many days it takes for us in order to get the average value of the amount of grass in the bin to be equal to it. Okay, so just a little few steps here, of course, remembering what average value is of the average value equation, and then setting that equal on the graph to make sure that we can then find it based off a crossing of the x-axis, something that is very standard and should be fairly easy for us with the graphing calculator. All right, let's go over to part D here. It tells us that for t being greater than 30, we have a new function L of t, the linear approximation of a at the t is equal to 30 mark, okay, is a better model for the amount of grass clippings remaining in the bin. Okay, so that tells us to use L of t to predict the time at which there will be the 0.5 pounds of grass remaining in the bin. All right, good. So we have to do a different kind of equation. We have L of t, which it tells us is the linear approximation. Something very important to note, as this is something that we can find, again, at a specific time at t is equal to 30. Right? If we want to do linear approximation, then we need to do a couple of things. Is that first, the equation is y is equal to m multiplied by x minus h plus k on the outside. And where h of k, h comma k is equal to, again, this is the a of 30, right? And we first need to find a of 30 on its own first off in order to find h and k, that ordered pair, for when we start on that approximation. Right? A of 30 then is going to be the 6.687 multiplied by all of the and make sure we show that, so 0.931 raised to the 30th power. Okay, so again, at the 30-day mark, there's going to be 0.783 pounds of grass left inside of the bin. And so with that, then we need to find m, right, where m is going to be equal to a prime of 30. Right? And linear approximation means that we need to find the derivative at that point to get started off, to start finding where the slope of the line tangent to that point is going to be, which is again done similar to our calculator that we've done earlier on this problem, meaning that we do the derivative function for our function, so 6.687 multiplied by 0.931, all raised to the t power. Okay, so all of this once more is going to be for the variable of t. Now for one point, that point being 30 on that function. Okay, so negative 0.056. 0.056 is going to be the pounds per day rate at which that grass is decreasing. And then with that, looks like we can put everything here together. So this equation is y is equal to the negative 0.056 multiplied by x minus the 30, because it starts at 30 days, and then plus k, so that's plus 0.783. And this is going to be k, this is going to be m, as stated right there. Again, just a very simple setup for the line tangent equation, right? Which, again, this is going to be L of t, as that is the equation to set that up. Okay, but that's not the entire problem. The problem then asks us to make sure that we can find, to use L of t, that there will be 0.5 pounds remaining in the bin, right? So in that case, if we want 0.5 to be the result of y, so we leave everything else intact because we are looking for the x, right? Like this, we can subtract the 0.5s on either side. Oh, it's 0.783. So we can subtract the 0.5s on either side to then make sure that we can then, once more, set it equal to 0, and then we gonna solve on the calculator. Okay, so with that, we can isolate x after we do that little bit of subtraction there, to then take a look at our graph once more. In this case, it's going to be copied down as a negative 0.056 multiplied by all of, again going back to x because we need to graph this on the xy plane, x minus 30, okay, all of that being added with, so if we want to make sure it's 0.783 minus 0.5. Okay, so all just like that. Okay, making sure we set our window properly because we're going beyond 30, so we can start at 30, maybe we can end at like 60, just to have a look to see if we can make that match. Again, we're making sure we're crossing the axis somewhere over there. Okay, so let's go ahead and trace it to find that 0. So moving backwards, making sure we're above the axis. So at 0.06, that's above the axis that we're looking for. And moving down, we need to make sure we go below it right there. Okay, so by making sure we get 35.054 if we round that properly. So 35.054 days, right, will be where, again, this is where we prove that L of t is equal to the 0.5 pounds that they were looking for, right, at the start of the problem. Okay, so just a few extra steps here for us to make sure that we understand how to do the tangent line, the linear approximation, right, the tangent line equation, as we go off in a single line with a single slope, and then with a little bit of plugging in for that 0.5 that they were looking to target, we can then find the amount of days that there will be exactly half a pound left inside of the bin. I'd say that's pretty good. So we should be moving forward to the next problem to then have a look to see what we can do next here. Okay. So question number 2 tells us that we have our graph here. So let me make sure we copy it over. It's a little bit ambiguous, but we should be fine. We have a horizontal line right there. We come in and we curl down like this. So that's region R right there. Okay. So they say let R be the region enclosed by the graph f of x being equal to x to the 4th power minus 2.3 x to the 3rd power plus 4, and the horizontal line y is equal to 4, okay, as shown, right? Okay, so we have the graph there and we have the exact functions set up right there. So part A tells us to find the volume of the solid generated when R is rotated about the horizontal line, y being equal to -2. All right. Okay. So we have that right there. So we want a rotational volume about y is equal to -2 instead, right? So with 4 being up there, right? So if you want to take that note, y is equal to +4 up there. We want to go somewhere down there where y is equal to -2, right? We're looking for the rotation on the part underneath there. Meaning if you want to find that, right, because this is going to be, again, there's a lot of space between here, right? Again, the empty space between the actual region R that's being rotated about that axis right there. Make sure we can show that it's being rotated down there, right? This is going to be done with the washer method in this case, right? So that means we set up, right, V being where the limits are going to be, and then we go for, and it's going to be big R squared minus little r squared dx, right? We're going by vertical because we go from the horizontal x values of the limits where we start and finish, so that's fine, right? And starting and finish are going to be somewhere there. We'll find those exact points in a little bit, but still, this is something to keep in mind, right, for ourselves as we measure the two different radii, right? One being the small r, then the other one being the large r, right, for the radius as this thing spins around. Okay. So with that in mind, let us go ahead and start looking at some of the possible ways to set this up so that we can start working our way through the radii. Of course, we need to know a and b, right? The limits of our integration. So with that, what we can do, of course, is that we can simply do some graphs here, right? So given that we need the f of x is equal to x to the 4th power minus 2.3x cubed plus 4 to be equal to 4, right? We need to find at which those cross. Again, this is the horizontal line, right? That this graph will be crossing. Then if we just move 4 over, we get x to the 4th minus 2.3x to the 3rd being equal to 0. Of course, a then being equal to 0, as you can see already on the graph, but as also seen on this way that we set up. Then we need to find the second intersection, and we will do that right on our calculator. Okay, so with the second part of that, we can set this up as this is going to be x raised to the 4th power minus 2.3. Let's make sure we keep that on the parentheses just to make sure, multiplied by x, which is raised to the 3rd power. Okay, so we have that function set up there. Make sure our window is set properly. We're only really going to go from what, like around like -1 all the way maybe to like 10. That's a good, I guess, for now. Okay, yeah, I see we have the cross right there. At least makes sense for what we're doing right now. So let's make sure we trace that in. All right, so at 4.5, let's see, are we moving down here? Oh, there you go. Make sure we're left side of that cross and then the right side of that cross. And we end up with the value of 2.3 being equal to 0 on that side as well. Okay. So at 2.3, we have our two limits of integration after doing a little bit of graphing on our calculator. And so now we need to find the big R and we need to find the little r to then plug in to our integral. Right? If we were looking for a quick description as to see what we're looking for, right? Big R is the total amount of distance, right? We're subtracting it by little r to then copy all of r that's going to be rotated about the axis. Something to make sure, of course, is that that pi coefficient must be there as part of a spinning, again, going on a circular motion across the axis. So making sure we have that there. So big R, again, is just going to be, if you look at it, it's a distance from y is equal to 4 to y is equal to -2. That's pretty straightforward and quite nice for us, meaning that we know that instantly from that distance is just a standard 6 going all the way across, right? Again, we're keeping that all the way through as we go down the entire. Although that's a full rectangle, then we're subtracting it by little r, right? That distance now instead. So this is now the distance from the, right, the bottom of the f of x to, now again, because we're keeping it, right, the values of f of x, now the distance from there, cutting it away all the way down to -2, right? Okay, so if that's the distance between those two, again, we're only measuring it vertically. All that really means is that if we need to make sure that we keep adding 2, because normally the values of f of x is just the distance from the point on that line or that function all the way down to the x-axis, we just need to keep adding 2 more to the distance, as that will take us 2 extra points down to y is equal to -2, right? So with that, we have r already set up as the value of f of x plus 2. adding 2 more distance to make sure we're measuring it all the way down to that dotted line over there. Okay, meaning that we can then set this up as the x to the 4th minus 2.3x to the 3rd plus 6. Okay, so with that, we can then finally put everything together here with the value of the volume v multiplied by pi going from 0 to 2.3. Again, big R is going to be all of 6 squared minus little r, which is x to the 4th minus 2.3x to the 3rd power plus 6 all the way to the 2nd power dx. Right? This is the proper way to set up inside of our calculator, and then we get our total volume to be equal to that. Right? So this now will be all thrown exactly into our calculator, and let's see what we end up with. Okay. So making sure that we do n9 for a function integral, right? We're integrating across this. So this is going to be, actually make sure before I forget here that we need to do a pi multiplication, right? Across here, right? So as a coefficient of pi waiting out there as the result of the integration to turn it into volume. So it's going to be 6 to the 2nd power subtracted by now all of the x to the 4th power. So we got x to the 4th power minus 2.3 times x to the 3rd power plus 6, making sure we have that plus 6 there, as we're adding 2 more to the heights across the values of the f of x, all raised to the 2nd power. Now we will take this for the variable of x, going from 0 to 2.3, as were the limits that were described right there. Okay, so again, 0 to 2.3 for that plus 6 right there, all that squared on each of those guys. And so we can then run that integration, and we get the result of 98.868. Okay. Makes enough sense, at least for the most part. And we have the entirety of 6 squared, right? So that's going to be, right, going all the way around, right? So 20, that'll be like 36, and multiply by the 2.3 again. But given that that is the radius multiplied by pi, we have to remove all of this section in the middle. So I think that at least that makes enough sense to make sure that we're keeping up with this problem. Okay. Then going on to part B, it then continues that region R is the base of a solid. Okay. For the solid, each cross section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Okay. And then we want to find the volume. Okay, so just to show what this is going to look like, as for a little bit here, so we have, if we want to show this as the y-axis and the x-axis, right, and we have that line coming across, and then we have the function of r right like that. Okay. Again, the idea being that we have a leg of a right triangle that's perpendicular to the x-axis. So we have one side going this way, one side going that way, one side coming down, right? And then we have a right triangle like that coming up, right? We can have a much smaller one right here, right? So something like this, again, on that side as well. Okay. And again, we need to make sure we capture the entire solid coming all the way across there, right? And so with that, that's going to be a new volume coming off of that, right? So equation-wise, we keep it still because it's still just going to be the region of R once more. This is going to be A to B, making sure we have a 1/2 on the outside because, again, volume of a right triangle means that's 1/2 base times height, right? So 1/2 base times height. And dx, because we are perpendicular to the x-axis, we are still measuring in terms of x going across on the limits on the x values. Okay, so with that, all we need to do then is to find the base and the height of this type of right triangle here. Again, base, of course, is that the leg of this right triangle being already the entire f of x, right? That vertical length between, hang on, we don't want to do that just yet. No, it's not, because f of x actually is the distance from the point to the end of that curve there. So that's one thing we need to make sure we're not going to do incorrectly. The base instead is going to be 4 subtracted by f of x, right? Just to show once more is that if we want to find the individual heights, so let me make sure I change the color here. Maybe this, do I have too many bright colors? Oh, let me try this one. I actually do have a nice bright pink right now on this nice pen here. Make sure we do everything come out. There we go. Okay. So again, r is going to be the distance from there to there, right? As shown in the pink right there. Okay. The main concern though is that this is not f of x, right? As you can see, if we show, right, maybe back in this, my standard black color, right? This is f of x, right? And we have y is equal to 4 up there. If we want instead the regions from only the ones described in pink right there to get the distance that contains r, it's going to be 4, right? Because the 4 being the entire distance from the x-axis to that line needs to be subtracted by f of x, so that all that remains, right, after we carve out everything underneath that line, that's what describes f of x, we then have only the heights remaining from 4 all the way down to the curve itself. Okay, so that's just going to take its own time. So it's 4 minus f of x for that. Okay, and then the height is going to be equal to the base as well, because it is an isosceles right triangle, meaning both the base and the height for this triangle are exactly the same. That's another 4 minus f of x waiting for us there. Okay, so with that in mind, we can then plug this back into the volume equation for us to then get ready to throw this into the calculator. So it's 1/2 going from 0 to 2.3. Now, because base times height multiplied together is going to be 4 minus f of x, all of this squared dx. Okay, and this is how we can find the entire volume. Okay, so with that, we can then plug this all right in there, right? Because it's going to be 1/2 multiplied by 0 to 2.3 on the limits of 4 minus all of the x to the 4th power minus 2.3x to the 3rd power plus 4. Okay? And all of this is still raised to the 2nd power dx. Okay? And this will then be thrown right into our calculator, and we can have a look to see what that volume will be like for this problem. Okay? So let's get started. So 0.5 is the coefficient waiting for us as a result of taking the area of a triangle, and then we're going to integrate this across from the entirety of 4 minus f of x, which is going to be x raised to the 4th power. Oh, make sure this is all closed inside there. So x to the 4th power like that, subtracted by 2.3 multiplied by x to the 3rd power plus 4. Okay, so all that closed off, then raised to the 2nd power to be integrated. Then we go take this from the limits from 0. Oh, sorry, make sure we tell the calculator that we're doing this for the variable of x. Then we run it through the limits of 0 to 2.3. Okay, 3.574 looks like it will be the case. Okay, 3.574. 3.574 will then be the volume instead. It should be a lot smaller, given the fact that we are only dealing with this very small space, right? No rotation, and just coming all the way across, versus the very large rotation for that. Okay, let's actually reset that playlist there, and it just likes to replay from last we left off. But there you go. Okay. So that does all check out for us, at least for a much smaller volume. But with that, we should be good to get to part C here. Okay, part C tells us that the vertical line x is equal to k divides r into 2 regions with equal areas. Okay. Now write but do not solve. An equation involving integral expressions whose solutions gives the value k. All right. So very interesting start to this problem. Again, so let's see if I can show this. I wonder, I'm running out of colors. I need to make sure I need to refill my pens again here. So I think started with this pink color. How pink are you? Quite pink. Okay. Well, we'll see if that can really show right here. But we're imagining that we have a vertical line, boom, right there. Oh, that's not too bad. So x being equal to k right there as part of that vertical line. Okay. Again, the idea is that it splits the two areas. It doesn't really show very nicely here, but we split the two areas exactly in half, right? Where both sides of the areas are going to be the same. What that means, of course, is that if we were to find the area of the region of k for us, that would then mean that they must be equal to each other because it split it directly in half. Okay, so the idea being that if we have the area of the region of R, right, the entirety of itself first is going to be, right, going from A to B on its own. Make sure that, again, similar to what we did in the previous problem, the 4 minus f of x, to make sure we capture just the region of R. Again, not everything underneath it. We have to cut that away from the function. So that's 4 minus f of x dx. Okay. And that is the area function to find the region of R, right? We want to say region of R right there. Okay. But again, we need to say that we're going to divide R into two regions with equal areas instead. Okay, so normally because we go A being from 0 and B being 2.3, again, K is going to be right in between. We don't know exactly where K is going to be, but that's exactly what we're going to try to find. So with that, right, and the entire area being cut in exactly in half, meaning that if we go then from 0 to K for this function, and then we add that with from going from K all the way to 2.3, the end of it, right? Again, that's going to be equal to the same thing already as well. Okay. On the other hand, of course, is that because we're splitting this directly in half, right, is that we can then say, right, that for them being equal to, so 0 to k of 4 minus f of x dx being equal to, let's see, we can just say it's equal to the other side, so k to 2.3 of 4 minus, why did I say k right there? F of x, oh man, what is happening back there? It's 4 minus f of x right there, and then dx on the outside. So let's make sure to clean that up on the next line of work here, right? So that's 4 minus f of x dx waiting on that side as well. Okay, so then if we just go ahead and solve for this thing to finish this off, is that, no, not solve, but to plug back in, right? That's 4 minus all of the x to the fourth minus 2.3 x to the third power plus 4. Okay, right? Dx being equal to, we can go about this another way too, right? Given that we already know what a of r is going to be if we just run the integral really quickly for us here, right? So we can run the integral of, let's see, so the entirety of x to the fourth, let's see, minus 2.3 times x to the third power, okay, plus 4. And again, this is going for the variable of x from 0 to 2.3. And all this multiplied by 1/2 to make sure we only get half of the area that was being looked at right here. So 2.99. Right. So then we can isolate one value of k on this side so that we can leave this as the answer, that if you're going to solve for k, that's going to be your result that you'd have to do, right? Again, 1/2 r being equal to the 2.99. Well, it should be a sub r. The area of that region r is going to be 2.99 from there. Okay, so that's the way that's going to go for now. Okay, and with that, we should be able to start correcting our work, and let's see if we can. And the idea here is that we're going back to 2014 exam here to make sure that we can answer this in a much better scoring way than what we had last time. So let me quickly go ahead and swap the screens over to show what that will look like. Okay, so we have right here, the 2014 scoring guidelines here on the right side. Actually, let me fix the camera a little bit here so this can be seen a lot nicer. Okay, right. So we have the scoring guidelines. So again, we have, starting with question 1, we can now compare side by side with the actual answers of this. So let me actually zoom in just a couple of steps here to make sure we're showing that all properly. Okay. So with that, we have on problem number 1, again, this is back going to the grass clippings equation, right? We have the A of t of any given pounds of grass at t measured in days. So with part A, they're asking for the average rate of change that was shown right there, right, over the entire interval from 0 to 30. And we need to show the units of measure with that. Okay, so what our paper then shows with our work, again, we set up exactly the way they want to, of the A of 30 minus A of 0 over 30 minus 0, as shown there at the bottom, which ends up as a result of negative 0.197 pounds per day. That is exactly going to be correct, right? So that's all good. That's what they want to see. So that's 1 out of 1 correct for part A. Okay. Moving on to part B, they're looking to find the value of A prime of 15, and we want to explain what that means in the context of the problem. Okay. So part B, of course, is that we have to run the derivative function, right, of 15, right, for A prime of 15 to be done properly, which by doing that directly to the calculator, negative 1.64 pounds per day is exactly what they want to see, right? The units do match, right? Pounds per day was the way that they wanted that to be expressed. Again, and that's going to be the rate at which the amount of grass is being decreased per day, as shown, right? The amount of grass decreasing at that rate at the time is equal to the 15 days. Okay, so with that, both of them are going to be correct with the interpretations. That's 2 out of 2 correct for us on part B. All right, moving on down to part C here. So it's going to be asking us for the time at which we get the grass, right? The grass on the average value of A of t being, oh man, the highlighting is not very good, but the average, I don't know if we can do this instead, right? Does it really show? Oh yeah, kind of, but maybe not. Okay. Oh, we can just draw normally. Let's see. I'm gonna trying to see if this can work. Let's go with like a kind of a darker blue here. This guy thick, and we gotta make sure we can see through it. There you go. Okay, I think that's a bit more like it. All right, so we want to make sure that we have the average value equation listed out right there, right? And for us, that is indeed going to be the case, right? The average value, we need to find the time at which that is going to be equal, right? For which is going to be, didn't exactly show us that it's the 2.753, but at the very end though, that does match the 2.415 or 14. Again, that's fine. That little change in the was it the 10,000s place is not really a big issue, right? This is still good enough, close enough for this answer to be correct. 12.413, right, is the time at which we can set the A of t equal to that same value that we found from the average value, right? So both setting up the average value equation and then the actual answer itself at the 12.413 days are exactly what they were looking for us to get full points on part C. Okay. Moving onwards to part D, then they asked us to find for that linear approximation instead, right, with L of t as a new equation, but that's a linear approximation of A at the time is equal to 30 days. So by doing that again, they did show exactly, they're using point slope form again here, just in a little bit of a different way right there, right, because that's going to be, right, the plus k as shown as the A of 30 right there, and then the t minus 30 inside, and then the slope, right, of A prime of 30, right, which we've done exactly right there, right, making sure we get the slope at the 30 days that they requested at the negative 0.056 as shown right there. That's A prime of 30 done properly. Okay, and then A of 30 as well, right, as shown right there of the 0.783. So with that, we end up with the 35.054. Again, that is indeed going to be the correct answer for the amount of days needed to get to the half-pound mark that they were asking for. Okay, so again, for us to show L of t properly as a setup as well as the actual equation, that's 2 points right there, right? Setting equal to 0.5 was going to be another point, and lastly, our answer at 35.054, that indeed will give us all 4 out of 4 correct for part A. Okay, very nice. So we haven't missed a single part of this problem number 1, meaning that for the start of our packet here, if you want to turn through that, okay, so something we can keep track of with all of our problems here, right? So questions 1 to 6, 2, 3, 4, 5, and 6. Okay, and making sure we're getting this out of 54. Problem number 1 is already 9 out of 9. A very good start to try to see if we can get a much higher score than we had last time, which was about 43 if I remember. So we got a lot to work on still. So let's move on to part 2, question number 2, for us to then get to grading this, right? So question number 2 included that graph of R, okay? And so let's get over to part A here. Okay, so the graph is already shown right there. Okay, then again, part A is that they want to find the volume, and we're rotated about y is equal to -2 on the horizontal line. Okay, the volume then is that, again, we want to make sure that we do show that equation properly. Let's try to circle that, right? Making sure we show that entire volume equation properly to make sure they understand what we're talking with here, right? Meaning that, again, as saying, was going to be big R squared minus little r squared. So when we set that up, right, that's going to be the 6 all that squared, right? 4 plus 2 as shown on the larger radius, as we make sure we're rotating about the y is equals -2 line instead of the y is equal to 0 line, right? We have to add 2 more units to that. And then the f of x plus 2, right? Which, again, I just showed that right there. Again, f of x plus 2 was shown on our piece of work there. Just to make sure we're actually going to plug that in directly to the calculator. We just combine it to a +6 and squaring all of that on the outside with a 98.868. Again, that's exactly the answer that they wanted to see. So again, we get 2 points to make sure we actually set the integral properly. The limits going from 0 to 2.3 was exactly correct. And so with that, we get all 4 out of 4 correct on part A. Very nice. Okay. Then moving forth on part B, we want to find, again, now instead the volume now. Instead, where we're going to have the cross sections in terms of the triangles instead coming across the region of R. My drawing is terrible on this mouse. But nonetheless, though, we do have to set up the volume accordingly, right, with the 1/2 of the base multiplied by the height, as shown here on the answer section. Meaning that because the base and the height were exactly the same, given that it was an isosceles right triangle, as stated right there, we then just have to square all that afterwards, right? So this setup of the integral is exactly correct. Then by plugging it directly into our calculator, we do get the correct answer of 3.574. That's exactly what we want to see. Again, 2 points for the integral, making sure everything's correct, including the units, or the limits, sorry, of integration, right? Starting and ending at 0 and then upwards to 2.3. So with that, that's 3 out of 3 correct on all 3 points on part B. All right. Lastly, ending at part C here. Again, we need to set up that equation, right? It looks like they just want to stop it right here, making sure that we go from, right, that line of k to make sure we split it exactly in half, right? So if we started and stopped those two integrals, right, from 0 to k and then k to 2.3, that will show that the entire region of R is exactly directly cut in half. And so with that, we do get the same areas of regions on either sides, and this is exactly what they want to see, right? So with that, okay, by splitting the area of the full region into areas of half regions right there, we do get 2 out of 2 correct, as shown, right, on this last part. Very good. So that looks like that's exactly what they want to see. Again, that's already in the line of work that I have right there. So with that, that's going to be another 9 out of 9 correct for part B. All right. So we are well on our way to making sure we can score a lot better than we have last time. So let's move on to question number 3. As a reminder, if we switch back over to the desk here, okay, as the bit of reminders that the questions 3 through 6 will not be using a graphing calculator, so we'll throw this one off to the side here as we continue forth on the rest of the exam. Okay, so last 4 problems, again 4, 5, and 6, are all not using a graphing calculator, so we'll not be referring back to that anymore as we move forth here. So question number 3, again, we're going to copy this down. We have a graph here and the question. So let's get that all copied down properly as we move on through this exam. Okay. So question number 3 then states that the function, well, make sure we have that graph first. Why don't we do that? So we go up, looks like 4, and down 4. So let's make sure we have enough space for both of that. Okay, so as we go across 5, did I do enough here? 2, 3, 3, 4, and 5. Then we go up 4, and then down 4. Okay, so -5 comma +2 is up there, -3 comma 0 is back there, and then 0 comma 4 is up there, and then 2 comma 0 is be right there, and then 4 comma -4 will be down there. Okay, so as a quick sketch here, we can go down, up, and down again, right? So that is going to be the section of the graph that they're talking about here. This, of course, is going to be the graph of f, as noted right there. Okay, so let's go over to the context of the problem. It then states here that the function f is defined on the closed interval going from -5 to +4. Okay, the graph f of f consists of 3 line segments. Okay, and it is shown, yeah. Okay, and it's shown right there. Okay, so now the next part here, right, though, is that we need to let g be the function defined by. Now we have g of x listed out here being equal to the integral going from -3 to x right there of f of t dt. That's going to be very important. We'll be sure that they're going to start asking questions about that soon enough. Okay, which really gets started with part A, with them saying we want to find g of 3. Okay, right off the bat right here, right? So we can sense right here that g of 3, as a note, is going to be the definite integral from -3 to +3 of f of t dt. Okay, so because we're taking the definite integral of f, again, this is now going to be the area under f, right? Again, now instead from the -3 to +3 limits for that integration, right? So -3 being that's going to be back here, right? -4 is all the way up there, right? So -3 to +3 is up there, okay? Right? Or, sorry, no, -3 is back here. What are we doing? Because -5 is all the way back there. Yeah, they told us already that the closed interval from -5 to +4. So -3 is right there. The tick marks are as follows, and then 3 is a little bit past that. Okay. So if you want to find this as area underneath the curve of f, that means that we need to split this accordingly, right? What we have right here is that we have obviously this very big triangle, right, as the first part going all the way across, and then ending at the small negative triangle, right, the triangle that's underneath the x-axis right there. Meaning that we can split this as the big triangle, right, minus the small triangle. Okay. Or we can do it as an addition of the negative triangle, but nonetheless, though, geometrically, that's what we're dealing with, and we can solve it as such because it is going to be the area underneath the graph of f. Okay. So with that, we can set everything up. Again, triangles, of course, being 1/2 multiplied by the base and height of that triangle. The base, of course, coming across is 1, 2, 3, 4, 5, just counting tick marks all the way across. From -3 to +2 is the entirety of that base of the triangle. So that's being a +5 base, and then a height going all the way up to +4 right there. Okay, as counting the tick marks, right, we're going up 4 spots to get to the peak of that triangle. Okay, so that's going to be the big triangle, and then we can then subtract it with the 1/2 times the smaller triangle, right, with 3 being, right, if we look down here, let's see, yeah, because we only go across 2 and we go down 4, right, so because we're going across 2 and down 4, again, this is going to be a slope of -2 for that segment going all the way down there. Okay, meaning that we have a base of 1 because we're only going from 2 to 3 for that mark right there. But then we then have to multiply that, right, with the height going down 2 units, and give me a slope of -2. So going across 1 means we go down 2. So we have -2, because then make sure we add that, because again, we're taking away from the negative heights from the total area, right, after everything is added up. So we just run through a little bit of easy math here. So we have 10 subtracted by a -1, subtracted by 1, that is, and then giving us a +9 as a result. Okay, that's pretty simple. Then going onwards to part B here, it will ask us on what open intervals let's see, contained in, going from -5 to +4, is the graph of G both increasing and concave down. And concave down. Okay, so if that's going to be the question, then we need to know, of course, what that means for G to be increasing and concave down, right? So G increasing, of course, would mean that the G prime of X must be greater than 0, and concave down means that, again, so concave down will then mean that the second derivative of G is now instead going to be less than 0. Okay? And obviously, because we're only given the equation of G and the overall graph of F, we then need to start putting that into order here, right? So G prime of X then is instead going to be equal to, by taking the first derivative of this integral here, right, using fundamental theorem of calculus, as something that we do know, is that when you take the derivative of an integral, only what remains is the original function inside the integral, taking the limit as its input, right, only for the one on the variable. Right, so because this there, that means fx must be greater than 0 for this first part, and the second derivative of x, by just taking the derivative again, means that the first derivative of f must be less than 0. Okay, so now we have this new relationship to go off of, right? So we can look at all the intervals in which these are going to be true, and we just simply transplant that back to the intervals that we're looking for here. So f of x being greater than 0, right, if we want to take a number line here, is that we go from -5 to -3. That's all above there. From -3 all the way to +3, and everything is negative after the fact, right? So going from -3 all the way to +3, right, that's all positive. Before that as well as positive, but after +3, as shown on the graph of f, we go underneath the axis. Okay. On the similar note here, we're now going to look at the first derivative of f, right? So instead of looking at just the position, again, this is going to be the increase / decrease, right? In this case, for being less than 0, decreasing is going to be our target for this. Okay. Noting, of course, that going up to -3, f is all decreasing, right? We're all getting closer to the axis from the top side to the bottom. So that's a decrease on that part. But going from -3 all the way to 0, right? That's all an increase and then a decrease after the fact. So from -3 to 0, that is an increase in values. But 0 going all the way down, right? It's all one straight line here, all the way down to the +4 on the x, right? That's going to be all decreases as well. Okay. So because of that, we have a few things to look over. Of course, is that from -5 to -3, that is all going to be correct, right? As it is both increasing and concave down for the value of G. But something we cannot forget, of course, as well, is that from 0 to 3, right? 0 is still underneath that positive of the increasing on G. And then going there from 0 all the way to +3 as well, +3 being inside of the negative of the second derivative, right? That's going to be another section right there in which we are negative on the second derivative, but also positive on the first derivative, right? So 0 to 3 as well, going to be another interval in which this happens. Okay, so then we can make that for x being, right? If we want to do, I guess if the open intervals, right? So it's -5 from x going to -3, and from 0 going to x to +3, right? And g of x is increasing and concave down. A bit of abbreviation there, but that's going to be our result of our analytical work shown right there. Okay, a little bit of number line analysis, but still something that should be fairly easy to come by for this type of problem. Okay, going to part C, it tells us that the function h is defined by h of x being equal to g of x over 5x. Okay, then we need to find h prime of 3. Okay, so very simple rules right here, again, meaning that, of course, with this being a division with both a function on bottom, again, this means that we just have to do quotient rule, right, as a result of this kind of derivative, meaning that, of course, we just need to go ahead and start doing that part. So again, it's the low, so 5x multiplied by g prime of x, subtracted by, right, the top function, so g of x multiplied by 5 as a derivative of the denominator, all over 5x all raised to the second power. Okay, simple quotient rule is something that should be very easily memorized by our students that are studying right now. Okay, so this is going to be h prime of x in the generic form. Okay, meaning that then we need to go ahead and go find the h prime of 3. So you plug in 3's across the board, meaning we have 15 multiplied by g prime of 3, all this subtracted by g of 3 multiplied by 5, all over 5 times 3, all of that squared. Okay, so we have all that set up right there. Okay, and g of 3, thankfully, we've already found earlier in part of the problem, right? G of 3 being equal to 9 since part A. So that's very good for us to put that through. Okay, and so with that, we can go ahead and start looking at these results here. So 15, oh sorry, also g prime of 3, 1 second here. So again, we already have the note that g of 3 is equal to 9, that's from part A. Okay, but g prime of 3, of course, is just going to be f of 3 as the relationship that we found earlier in part B. So given that we're looking at f of 3 set up right there that we've seen before is -2. Okay, and that's g prime of 3. So by plugging everything in here, that's 15 multiplied by -2 as a result of g prime of 3, subtracted by a regular g of 3, which is a 9 multiplied by 5, all over, now that's 15 squared. Okay, we can go about a little bit of simplification if we want to. Makes our life a little bit easier. We can simplify a factor of, well, this 9 times 5 is also another 15 times 3, so we can take off a factor 15 on everything here, meaning that we get the fraction left as -2 subtracted by a +3 all over a whole 15, giving us -5 over 15, a -1 over 3 as a result. Okay, again, just a little bit of a reminder of what quotient rule is and how to do that, of course, by taking the derivative of h of x when we started with, but by running through all the work properly, we get a nice fraction just as a result there. Okay, ending at part D here, it tells us that the function p is defined by p of x being equal to f of x squared minus x. Okay, then it tells us to find the slope of the line tangent to the graph of p at the point where x is equal to -1. Okay, very good. So with that, we have ourselves here the entire equation. Now p of x, again, we want to find the slope of the tangent line where x is equal to -1. Okay, so if all we need to do is just find the slope of the tangent line, of course, all that they're really asking now is that we just need to find p prime of -1, right? That is what they are truly asking for, just in a little bit of a convoluted way, right? Just to see if they're keeping us on our on the edge here, right? Of course, meaning that y is equal to x minus h plus k. Again, all that they're asking for, because this is the tangent line, right? All they're asking for is just m, which in this case is going to be the p prime of -1. Okay. So with that, with the clear understanding of how we don't need to do any bit of extra work here, is that we just find the p prime of x, okay, which means that we just need to take the derivative of f of x squared minus x, meaning that using some chain rule, right? Again, keeping track of chain rule as we're taking the derivative of a function with many things inside of it, that it's going to be 2x minus 1 multiplied after the fact. Okay, so going back, if it's p prime of -1, that means it's going to be f prime of the -1 all that squared minus another -1, plugging in properly, making sure the signs are all there, and then all that multiplied by the 2 times -1 minus 1 there as well. Okay, so with that, we just gotta go ahead and start simplifying this so we know exactly what we need. So it's gonna be f prime of, now this be positive 1 there, subtracted by negative 1, so that's another positive 1, that's f prime of 2, and then that's all multiplied by 2 times negative 1 being negative 2 right there, subtracted by 1 making it negative 3. Okay, so this is the line of work that they want us to do right here. Okay, f prime of 2 then going to be, right, so at the point of 2 right there, right, as you can see on the graph of f, set up right there again, it's going to be the slope of this entire line, which we've already calculated before, right? And given that we've gone across 2 and down 2, that this is the slope of negative 2 for that entire section, including the positive 2 right there. Okay, so with that, we have negative 2 multiplied by a negative 3, giving us a positive 6 as p prime of negative 1. Okay, very nice, very easy bit of work there. Again, just a little bit of simplifying and making sure we're on the right page about that. Okay, so this will be saving as we go to part number 4 here, and then we'll again grade those two parts together. Okay, so we have here on part number 4 is that we have a nice table right here, which we'll copy down. So this is going to be measured in t in minutes, and then we have VA of t, and this is going to be meters per minute. Okay, so because we have that table set up there, right, the minutes will be 2, going from 0 to 2 to 5 to 8 to 12. Okay, and we go from 0, 100, 40, negative 120, and then negative 150. Okay, all right. So we have all of this set up right here, right? So then the context, of course, for problem 3 is going to start here that train A runs back and forth on an east-west section of railroad track. Okay. Train A's velocity measured in meters per minute is given by the V of A of t, okay, where t is in minutes. Okay, and they give us from that table right there. All right, good. So let's go to part A right here. So it tells us to find the average acceleration of train A over the interval going from t to 8. All right. Okay, so given that they want to find average acceleration, right, with train A, okay, now from the interval from 2 to 8, of course, meaning that if we want to look at the relationship, right, acceleration of any sort of function, right, this for train A means that it's going to be the velocity of train A with its derivative in respect to time. Okay, right. So if we want to find average acceleration, of course, this is going to be average rate of change, right, for V of t, right, that function that we started out with the table on those values set up right there on top. Okay, so we can set up that average rate of change then as part of, they gave us a limits from 2 to 8, meaning that we go from the velocity of A at 8 minutes subtracted by the velocity of A at 2 minutes, all divided by 8 minus 2. And a very simple setup for average rate of change right there. And then we just plug everything in. So V at 8 is the negative 120 as listed exactly on the table, subtracted by VA of 2 with a 100 over there. Now all that divided by 8 minus 2 being positive 6. Okay, so we get negative 220 looks like. Okay. Yep, so negative 220 all over a positive 6. I don't think that's divisible by 6. No, that's not going to be. So we're just going to leave it in terms of an improper fraction of negative 1/10 over 3. Now, given that this is going to be acceleration, right, a change in velocity respect to time, that's going to be meters per minute squared in terms of the units. Okay. And we can leave it just exactly like that. Okay. Let's go over to part B here. So it asks that, should be does the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t, with, again, the interval from 5 to 8 minutes instead. Okay, so looks like they want us to confirm the specific conclusion, right, that we have a specific velocity at negative 100 meters per minute, right, in between the limits from 5 to 8. What does it sound like, of course, is that because we're trying to conclude that, right, that we have to get to some velocity at negative specific, right, again, is that we have a specific v of a, right, again, equal to some number. They give us at negative 100, okay, and we only have values of v of a, right, on that table. Again, we're looking to see if I can confirm that negative 100, again, that number value that they're talking about is going to be confirmed. This means that we're going to be using IVT, the intermediate value theorem, right, to prove that we are going to cross that negative 100 as a result, right? Given that v of 5, right, va of 5 is equal to 40, and va of 8 is equal to negative 120, and we know that the velocity is going to be continuous, right? So because v of a is continuous, right, from the interval 5 to t to 8, and IVT confirms that the train will have a velocity of negative 100 meters per minute, right, in the interval 5 to 8. Okay, right, very simple, right, knowing that we're going to cross from 40 to negative 120 in a continuous manner. So we have indeed confirmed that that is going to be the case. There must be at least one t in which that is going to be crossed because of its continuous nature. All right, very nice. Okay, then it will continue that at the time is equal to 2. Okay, the train A's position is 300 meters east of origin station. Okay, and the train is moving east. Okay, and then it tells us that we want to write an integral expression involving an integral that gives the position of train A. Okay, in meters from the origin station at the time is equal to 12. Okay, then it continues to say that use a trapezoidal sum with 3 subintervals. Indicated by the table. To approximate the position of the train at the t is equal to 12. Okay. We've got a lot going on here, which we need to decipher really quickly as we go through this problem. Okay, so we start at 300 meters east at time is equal to 2, and we keep moving east away from the origin station. Okay, so because we give, moving east at time is equal to 2, then something, of course, is that the positive values then are going to be moving east, and negative values means we're moving west back towards the origin station. Okay, so because of that, we need an integral expression, right? We need to give the position of train A, right? And at t is equal to 12. That's the time that we want to see. Okay, then we will use a trapezoidal sum with 3 subintervals then to get that position at the 12-minute mark. Okay, so because of that, if we know that we're going from 2 all the way to 12 as our limits here, that of course will then mean that that is going to be our limits of integration, right? Going from 2 to 12 of the velocity of A of t in respect to time, right? The velocity of the train at t. Again, this means that the fundamental theorem of calculus will then hold, that we are going of x, right, position-wise of 12 for the train A, subtracted by the position of train A at 2, right? Again, going back integral-wise by the integral of the velocity, by removing one instance of the time aspect from the velocity units, we go back to directly to position. And because of that, if we want to then isolate for the position of train A at the 12-minute mark, that must mean that we then take the position at 2, again we're moving that over to the right side, added with then the integral going from 2 to 12, okay, of the v of A of t dt. Just like that. Okay, so we can then move forward through this, right? Again, this is going to be with trapezoidal. The trapezoidal sum, again, they want 3 subintervals as described in the problem, and the position at 2 they already gave us at 300 meters east. Okay, so meters plus, now with trapezoidal sum, of course, means that trapezoidal approximation will indicate that it's going to be area of a trapezoid, right? Meaning that it's going to be the base times, now with the trapezoids, of course, meaning that we have 2 different heights, so that's going to be height 1 plus height 2 all over 2, right, as the average of the 2 heights, to make sure that we can then end up with a proper area of the trapezoid with 2 separate heights going vertically. Okay, so then we need to add that all up with what we have here, right? 3 subintervals means that we go from 2 to 5 as one interval, 5 to 8, and then 8 to 12. Those are 3 subintervals listed out right there from 4 points, and we keep track of all those heights accordingly as well. Okay, so with that, we then have the first base going from 2 to 5, so that's a base of 3, multiplied by all of the average of the 2 heights, so it's 100 plus 40 all over 2, and that's the first trapezoid. Our second trapezoid then goes from 5 to 8, so that base is still 3, and our 2 heights is going to be 40, and keep in mind that we're adding a negative 120, as that is the height, again going the opposite way at the 8-minute mark, so we keep that in mind there as well, and divide it all by 2. And lastly, we have our third subinterval. So 8 to 12, sorry, has a base of 4. And we're going from 8 to 12 minutes. So we keep that in mind that we're not going to have the same base of 3. And then we will have the average of negative 120 plus the negative 150. And all that divided by 2. Okay. So we have all this set up here to be isolated for the position at the 12-minute mark. So we can leave the 300 meters right there as we start solving all across here. So 3 times 140 over 2, right? So 140 then is just going to be 70 after removing that 2 there. So we get 210 as a result there. Then 40 and negative 120 is a negative 80. Then dividing that by 2 makes it a negative 40 times a 3 makes it a negative 120. Then negative 120, negative 150, but because we have a 4 that's a coefficient, we can easily cancel that out to make it a positive 2. So negative 200 and, oh, that's not it actually. This is negative 270 down there. Multiplied by 2 is a negative 540. Okay. All right, a very simple math just to keep everything moving along smoothly here. And so with that, we just have to then go and simplify everything, meaning that we get 510 minus 120 minus 540 as a result from all of that setup right there. 510, 540 makes a negative 30, so we end up with negative 150 as the last bit here, and this is going to be meters. Okay, right, so negative meters doesn't exactly make the most sense, but of course, given that positive meters means that we're east of the origin station, right? Negative meters will then mean, right, from the start of the problem, we're going to go the opposite direction. So this is going to be 150 meters west of origin station at the t is equal to 12. Okay, and that's what we end up with right there. Okay, so we're out of space already on this single page, but that just means we got to flip this over to the back for us to deal with part D here as we finish up problem number 4 before we get to our corrections here. So part D tells us that a second train, okay, again, train B, okay, travels north from origin station. Okay, and then at time t, okay, the velocity of train B is given by this equation, to put it down here, so B of t being equal to negative 5t squared plus 60t plus 25. Okay, and at the t is equal to 2. Okay, the train is 400 meters north of the station. Okay, then it tells us to find the rate. In meters per minute, okay, at which the distance between train A and B is changing at the time is equal to 2. All right. So this one is quite the doozy here because we have to find the distance, right? So it tells you at the very end the distance between train A and train B. But of course, one thing to note is that our main issue is that if we want to write this out, right, if we have origin station right there in the center, right? So origin station. Okay. Our main problem is that we have, right, we have train A going on east to west only, right? If I want to really write on directions, right? Right. Train A is only going east to west direction-wise, while train B is going north and south, right? So would you look at that, right? Our distance is now determined by the Pythagorean theorem. Oh my, right? We have to do a diagonal distance across these two trains, okay? And we do have the velocity of B, so that's something to keep note of here, right? But the main issue, of course, is that our main distance then is going to be the actual, right? So if you want to make sure that the distance, right? If we want to put this into perspective, I wonder if we can use, let's just use the variable d here, right? The distance between A and B, right, is then going to be, right, the square root of B squared plus A squared, right? Again, this is the distance of the two trains, right? Okay. The main issue, of course, is that we don't want the actual distance itself. We want the changing distance at the time, right? The distance between the two is changing at a specific time. Meaning we don't want just the distance. We want the change in distance with respect to time at the time is equal to 2 mark. Okay. Now this is going to be quite the problem to contend with, but nonetheless though, remembering that again, this is going to be the distance from origin, right? Again, for both B and A, That's something that we already know. Again, we're going to keep that as the, instead, just to keep everything the same, is an x of b of t, all this squared, plus x a of t, all that squared. Okay, so we have position functions that we need to keep track of, and then getting us to the actual distance between the two trains. Okay, but now we've got ourselves another issue. Okay, all right. So the next point of contention here is that then we need to go ahead and start taking the derivatives, right, so that we can get d of d over d of t. Okay, so with that then, we have to go and take, right, by taking the first derivative of this whole equation there in the inside of that square root. That means that we have to go and start doing quite a bit of, right, chain rule in this business, right? Okay, of course, noting that by taking the derivative, right, of any sort of position, that would mean, right, by taking its derivative, that means it goes to the velocity of that guy instead. Okay, so because of this is all in the square root, we leave this as the 1/2. Again, now all this is now thrown underneath as the x squared b of t plus x squared of a of t. Okay, right? Simple square root rule, but then again, chain rule is then going to come right in here and start throwing in a lot of coefficients for us, meaning we have to take the derivative of everything inside of that square root, meaning that we have to go bring this down as 2 times xb of t, right? Then we're not done there, because then we have to multiply that by the velocity of b, or again the derivative of x of b. Chain rule goes through one more layer as well, so multiplied by the velocity of b, and the same will apply with the same thing on the other side with the position of a multiplied by the velocity of a. Okay, and all that is thrown in there properly as such. Okay, this is a lot to contend with, but nonetheless, though, all we need to do then is, because we've already isolated the change in the distance between the two trains already, we just need to then plug in for 2 on the time through all of this. Thankfully, we have all the space right now to work with that, so that's going to be 2 multiplied by x of b of 2 times the velocity of b of 2, okay, and multiplied by 2 times the x of a of 2 times the velocity of a of 2, that is. Okay, then we divide that all the way through. Then we have 2 over the square root of the x squared of b, and then at the time of 2, and then x squared of a at the time of 2. Okay, so this is a lot of plugins to do, so let's actually list out point-wise what we're dealing with here, right? So at the position of 2, we need to know that of b, and as well for train A, right? And then now we need the same thing now about the velocity of train B at time of 2, and the velocity of train A at the time of 2. Okay, now velocity of train A at the time of 2 is already given exactly from the table at the start of the problem. That's 100 meters per minute. Quite nice. Okay, the position at train B at 2, right? They told us already at the start of the problem as well. It's 400 meters north. Again, given that north and east are the positive values of our coordinates right there, meaning that that position at train B at the time of 2 then is going to be 400 meters positive. Okay, and then the position at train A, do we have that one already? Let's see here. Yes, this is from part C. So actually beforehand, part C already told us that train A position is 300 meters east, right? That was already from part C. So that's something that's very nice for us to refer back to. And something that's already stated for us as 300 meters. Again, east was already defined as our positive direction for these two trains. And then lastly, all we need is a velocity at the train B at 2 minutes, which of course they gave us as the equation right there. So let's go ahead and plug in for that, and then we can start plugging into this grand scheme of the first derivative. So at the 2 minute mark, giving us -5 of 2 squared plus 60 times 2 plus 25. A little bit of work here, so -5 times a positive 4 makes it -20. 60 times 2 makes it a positive 120, and then plus 25. So -20 and positive 20, giving us, adding with 25, makes it 125 meters per minute as the velocity of B at the 2 minute mark. Pretty straightforward there. So let's go ahead and close this thing out by plugging everything we need into the change in the distance between the two trains, respect to time, at the t is equal to 2 mark. And so with that, we start plugging everything in. So it's 2 multiplied by the distance of train B is 400 meters, and then the velocity of train B is 125 meters per minute. Okay, and then we have all of 2 times now the position of train A is going to be 300 meters. Okay, and then that's multiplied by the velocity of train A, which is 100 meters per minute. Okay, and then all this then needs to be divided by the result of 2 multiplied by the square root of x of b squared. So that's the velocity of b squared. So that's going to be 400. So all of 400 meters, all that squared, plus the x of a squared. So the position of a squared is 300 meters, all that squared. Okay. So something to note here, that before we start having to deal with all these crazy zeros all inside of our square roots, is that given the fact that it's 300 and 400 on the 2 sides of our triangle here, right? Again, to show the illustrator one more time down here, right? Given that we have 300 on train A and 400 on train B, that just means that the actual distance, which is going to be that squared in there from Pythagorean, that's Pythagorean theorem, right? Of course, this follows exactly in the steps of a 3, 4, and 5 triangle. We just have 2 zeros slapped on it, right? 300, 400, 500 is indeed the right way to set up for Pythagorean theorem right there, right? Meaning that we can then ease up that denominator. We can first cancel out 2's across the board right there. That's pretty simple. Okay, so because this ends up as a nice 500 there, we can then ease up with taking off a pair of 2 zeros from both of these guys right there, meaning we end up with 4 times 125. That makes it exactly 500 on the numerator, plus then all that's left is just 3 times 100. That's 300 all over 5, right? So that's going to be 800 over 5, which gives us a, let's see, 160, right? And that's going to be meters per minute as its distance over time as a result between the 2 trains. All right, so quite a bit of work there on our side. Again, none of which needed a calculator. All of it was just simple work, and of course keeping track of the implicit differentiation. Again, we're doing the change of Pythagorean theorem over time, right? We could have done that a few different ways, but nonetheless, this is at least for us, the way to ensure that we get a proper answer after taking the problems. Yes, wow, our reliable viewer, Mijin, does say that I am a genius based off this problem. Well, for one, this is actually a redo. Again, for those who come in late, this is actually a redoing of the 2014 AP Calculus exam, something that we actually have not scored very well the first time that we've done it. But by doing this again, we are definitely learning from our prior mistakes. I actually got this problem wrong the last time, but now this is actually the perfect timing for us to go and correct ourselves to see how well we scored across both problems. Okay, you're good. So starting with question number 3 here, let's go ahead and move this back to our corrections here. So let's change the screen right here. Okay, so let's move down to question number 3 since we're continuing here, right? Again, the graph is copied over. This is the graph of f, and they gave us the g of x equation, right? G of x being equal to that definite integral of f of t dt. So with that, we're going over to part A, which is going to find g of 3 on its own, which, as stated with our problem, is just going to be plugging right in for the definite integral from -3 to +3 f of t dt. And then, because we're finding the area underneath the curve, we end up with a +9 after doing a little bit of subtraction right there. And that's going to be 1 out of 1 correct for that problem. Okay. Then, on the open intervals, so on part B, they asked us to find where it's going to be both increasing and concave down, right? That is something that was to be noted, right? Because increasing then meant that the g prime of x is greater than 0, and concave down meant that the g double prime of x is less than 0, as stated right there. Okay, so because of that, we made the same relationships with the f of x, right? By taking it back one step, f of x was related to g prime of x, and f prime of x was related to g double prime of x. So because of that, we do get the two sets of values here, from -5 to -3, and from 0 to, why did I say 3? It really should have been 2. What am I doing? Okay. Well, that's unfortunately one ding on our part, because it's supposed to be all the way to +2 instead of 3. Which was already written out for us earlier on the graph, which is a little bit unfortunate that we missed that. We even showed the 0 right there, which in this case would have stopped at 2 on the original function, and then, right, that would have been 2 on that sense for us to make sure that we're going that way instead. Okay? So our reasoning is correct, actually, because we wrote the right expressions going from f to g in terms of that consideration. So in this case, this is only going to be one of the two correct. We did not get the correct answers, as we should have, to show the right amounts of intervals in which that was going to be true. A little bit unfortunate we made a silly mistake there, but let's try to see if we can get everything else correct on this part instead. Okay, so part C is going to be finding h prime of 3 as shown right there, meaning we have to go and do quotient rule, right, as shown right there, right? And we have that exactly listed out the way that we should have, right? 5x times g prime of x minus g of x times 5 all over 5x squared up there in the denominator. All right, so by running everything through and all the work, right, and showing that we can do quotient rule properly, and a result of -1/3 as the proper answer, that is indeed going to give us 2 out of 2 correct on part C. Okay, well, sorry, it's actually 2 points for h prime of x. That's 3 out of 3 correct. Oh, they very interesting. They weighed h prime of x, actually just remembering quotient rule as 2 points from here. But nonetheless, though, that's the way that they want to do it. So let's finish off with the part D here, which again they were asking for p prime of -1, as you can see as part right there. We just have to run chain rule properly of the p prime of x as shown right there, which we do have exactly lined up right there. F prime of x squared minus x, all multiplied by a 2x minus 1 on the outside. So again, that's 2 points for them, for us to know how to do chain rule properly, and then our result as +6 as a p prime of -1 after plugging everything accordingly. So that's 3 out of 3 correct there as well. Okay, so we unfortunately did take one miss there with that little issue from a 3 and a 2, but nonetheless, though, that gives us 8 out of 8 correct, 8 out of 9 correct for this entire part. And let's record that as such on the start of our packet here, as we tally up our totals at the very end here. So that is 8 out of 9 on question number 3. So let's go on to question number 4 before we finish the last third of this exam. Okay. This is question number 4. Again, we have that table of the train speeds, right, as shown right there on question number 4, right? So with part A, doing average acceleration, meaning that average acceleration is going to be the average rate of change for the velocity function. And we set that up exactly. V of A of 8 minus V of A of 2 all over 8 minus 2. So running that through, that's going to be the 110 meters per minute squared, right? Okay, so that is exactly what they want to see in terms of the average accelerations. That's 1 out of 1 correct. Okay. The negative, right? Then right there. So, oh, that's really hard to see on the screen, isn't it? So there's a negative there, but it might probably be so. That's negative 110 over 3 meters per minute squared. Okay. Then we have part B here. So part B is saying that we wanted to confirm that we can get a velocity at a specific time at negative 100 meters per minute, right? At any time of t between the 5 and 8 limits of the time. Okay. So again, they did include back to intermediate volume theorem because the velocity is continuous over the entire time frame. So again, IVT, that's intermediate volume theorem, will then confirm because we're crossing from positive 40 to negative 120. Again, they did state that, right? Negative 120 to positive 40. The train is moving between those two different velocities. So negative 100 must be in between there, and it must cross at any specific time. So because of that, right? Because we've shown that that's going to be the case and our reasoning is correct, that is going to be 2 out of 2 correct for us on that part. Okay. Moving down to part 3. Then we have the issue that we want to find, right, the position at the 12-minute mark, right? Meaning that, again, thanks to fundamental theorem of calculus, we do have this exact kind of separation right there, shown on the right side, right? I used x because that's the position, at least in my case. So the x at 12 is going to be the same position at 2 added with that definite integral, right? Of, well, it's going to cut off right there. So let's recircle that, right? Because this is the definite integral which they want to see, right? Of VA of t. Again, using fundamental theorem, knowing that definite integrals of the velocity will get you back to position. So with a little bit of substitution and running the proper trapezoidal sum as the, again, the base multiplied by the average of the two heights right there, which all of our work does show that properly, all spread out here on the bottom there. Okay, we then end up with the exact negative 150, right, as stated right there as a result of our integration. Then that means that position of train A is 150 meters west of the origin station. Again, we make that note as well with the negative results of our distance, meaning that we are west of the station at the 12-minute mark. Okay, so again, showing the actual position expression properly of isolating the position at 12 minutes, then running the actual trapezoidal sum of the correct equation, and then the actual position, all three of them will give us 3 to 3 correct for part C. Okay, then let's conclude here with part D. Again, that really hard problem right there, which we were going to do that position of A and B, right? Meaning that we did have to do the Pythagorean theorem between the distances between B and A trains, right, going east and north between those two, right? Now the testers, the exam here, they just decided to run the indefinite, or they wanted to run the implicit differentiation across the entire Pythagorean theorem. On the other hand, they did of course note that the diagonal was 500 as was shown in the last bit of work right there. But nonetheless though, by running the implicit differentiation, right, the work is still going to be correct by isolating for the actual distance between the two, right? And they ran the work really crazily. I just did a lot of simplification, right? But we do end up with 160 meters per minute. Again, they want to make sure we do implicit differentiation of the distance, which is exactly what we did here. Again, that's why it's the d of d, the distance in respect to time. That's what they were looking for. So again, they don't exactly show that kind of line of work here. They ran it a different way. I might need to remember trying to do that next time. But nonetheless, though, the work that I've done on my side was just to isolate for the change in respect to time. So I just threw everything up in the denominator and then we plugged in accordingly. But nonetheless, the answer was exactly correct at 160 meters per minute. And that is exactly what they want to see, giving us all 3 out of 3 correct for part D. Okay, so because of that, we end up with the total of 8 out of 9 again. No, not even 9 out of 9 actually. We got everything correct, right? Going from part D all the way back to part A. Everything was indeed correct the way that it should have been. So we get another 9 out of 9 there. Well, that problem I remember was quite the hard one when I first did it, but thankfully we've actually managed to redeem ourselves with getting full marks on it this time around. Okay. So with that, let's go ahead and get to the last 2 problems on this packet, and then we shall see how our improved score will be since the last time we've taken this about a month ago. Yep. Make sure we don't show that. We want to make sure we show our desk here, and with back to our packet again, as we have another table to copy down. Okay. So we have ourselves a table between the x values. So question number 5. So we have f prime of x there, then, oh sorry, we'll start with f of x first, then we go down f prime of x, then we go g of x, and then we go g prime of x. Okay. So we got all of these guys listed out right here. Okay. Then we go down as to their values. So at -2 being the x, we have 12 on the f, -5 on f prime of x, -1 on g of x, and +2 on g prime of x. Then moving down, we have then the interval going from -2 to x to -1. Okay. They're telling us that it's positive on the interval there, negative for f prime of x, and then negative on g of x, but positive on g prime of x. Okay. And this table continues. So then we get negative 1 on the x, so we get 8, 0, 0, 3 over 2 in that order. Okay. Then we go from the interval from negative 1 to x to positive 1, making it positive for f of x, negative on f prime of x, and then positive for both g of x and g prime of x. And then finish capping everything off here. Oh, not quite actually. We go to positive 1 on the x, giving us 2, 0, positive 3, and 0 in that order. And then we have one last section, one last two sections here. So we go 1 to x to 3. And then it's going to be positive on f of x, positive on f prime of x, positive again on g of x, but it's going to be negative on g prime of x. And then lastly, finishing this table at x of 3 is going to be 7, 1/2, 1, and negative 2. All right, so we finally got all that copied down properly as something we can refer back to. So as context here tells us that the twice differentiable functions g and f are defined for all real numbers. Okay, numbers for x. Okay, and they give it to us on terms of that table right there. Okay, very interesting. So getting to part A here, it tells us that they want to find the x coordinate of each relative minimum of f on the interval -2 to +3. Okay. All right. Very good. So relative minimum then is that if that's going to be their request, will then mean that mathematically that will mean that the first derivative of f, right, must be going from positive minimum, that is, so other way, so it's negative going to a positive, right? That change in sign on the first derivative of f is exactly what we need to see. Of course, I don't put the positive sign directly in the circle right there, right? Negative to positive, you want to make another note there, is the shift that the sign must have for this to be mathematically true. Okay, so because we're going from -2 to +3, right, we have the entire table to work with, right? As you can see, we have for the first derivative of f, right, we have -5 going to negative to 0, but then goes back to negative as you follow that line, right? So from -2 to -1 is -5, 0, right? So -5 down to 0 if you want to make a number line right here, right? Given that we're analyzing for f prime of x. So starting at -5 and going to 0, right? It's all going to be negatives all the way through until we hit 0, right? That's going to be x at -1, right? So that's going to be 0 there. It's just keeping there at the point right there because it's neither positive nor negative at that point. But then going from -1 all the way to +1, it's negative once more on the interval as shown on the f prime of x line right there. And then we go to 0 again at +1. Then from 1 to +3, we get positive right there, and we keep it as such the rest of the way. Okay, so given that this is the number line for f prime of x, the only relative minimum that's there is going to be at the x is equal to +1 because we do shift from negative to positive on the sign for the first derivative, while on the other hand at -1, it goes from negative and stays negative. Therefore, it cannot be a relative minimum as per the definition. Okay. So because of that, we then will then prove that, right, the f of x has a relative minimum at the x is equal to +1. Okay, our number line analysis will show that as well. All right, yes, we have Eric coming in the chat telling us that we are showing all the steps. That's very good that our viewers can see that as well. And so with that, we can definitely take this into account. Again, we have the number line analysis to show exactly what relative minimums are going to look like based off the first derivative. And with that, we can go over to the part B of this equation. Okay, so this problem, then part B, tells us to explain why there must be a value C for the interval going from -1 to +1, such that f double prime of C must be equal to 0. Okay. All right, so we have ourselves this interesting note right there, right? So from -1 to +1 on the second derivative equation. Okay, so with that not being there, right, as you can see, this only goes up to the first derivative on the table. We then need to go and take the note as to what the second derivative then must be, right, going from -1 to +1. Right. Of course, we can easily see though that the same interval from -1 to +1 is all negative from the first derivative, right? So the first derivative going from that exact interval is all negative, but as you can see, it starts at 0, goes negative, and goes back to 0 again. Okay, so something that we must note here, of course, is that if we wanted to draw a simple graph here, right? So the first derivative, if you want to graph that out again, we're going to be going from 0 at the so at -1 and going to +1. So we start at 0 right there, then we go negative and we go back up, right? As you can see here, right, because we're crossing between two zeros from -1 to +1 for the first derivative, they're asking to confirm if the second derivative will then have some value equal to 0 along that interval. Okay, but of course, one thing already known as Rolle's theorem, right? Theorem, or in any case, is going to be an extension of mean value theorem as well, right? Given the fact that because, right, the first derivative of -1, so the first part of the interval, right, is going to be equal to 0, and the second part, the ending part, so f prime of 1 as well, is also equal to 0, as shown on the table right there. From, again, -1 on the first derivative of f is 0, +1 on the first derivative is also equal to 0. So because of that, right, that part shows on Rolle's theorem. Okay, right. Rolle's theorem confirms that there must be at least one C in that interval from -1 to C to +1, right, such that the second derivative, so now the derivative of that function between those two parts, must be equal to 0. Right? As seen in this little diagram down here, again, we have at least one point if we're keeping a continuous function, right? Given that that's already stated for the start of the problem, is that by going all the way through, is that you must have at least one horizontal tangent line if we start and finish at the exact same y value. Okay, so again, we're using a little bit of an extension of mean value theorem known as Rolle's theorem. That's something that should be officially known by the students here, which my pen is acting up on me. But in any case though, this is going to be the situation that we are dealing with for this problem right here. Okay. Then going on to part C here, it tells us that the function h is defined by h of x being equal to the natural log of f of x. Okay, then it tells us to find h prime of 3, and we need to show all the work for. Okay, so h of x being equal to another part of a different function, of course, this will mean that we must be abiding by chain rule as a result of our work here, right? Because by taking the first derivative of h as such means that we have to take the derivative of the natural log first, meaning that we take 1 over f of x, again using the natural log rule as something that we must keep into account here. Then we need to multiply by the derivative of the inside, which is the f prime of x. Okay, So with that, right, this will just simplify easily as the ratio between f prime of x over f of x, which then we will then go ahead and plug back in for the h of h prime of 3 that they were asking for as f prime of 3 over f of 3, listed down as such. Then all we need to do is refer back to our table here where we have the x values of 3 listed up there. So f prime of x is equal to 1/2 and f of x is equal to 7 from those x values. Okay, so with that, that's going to be a positive 1/2, keeping track of each of them, and then divided by a whole 7 for f of 3. And with that, we just have to simplify this fraction, 1/2 divided by 7, making it 1 over 14 as a result of h prime of 3. All right, fairly straightforward on that one. Then let's go ahead and conclude problem number 5 here that they want us to evaluate this expression here. So the definite integral from -2 to +3 of f prime of g of x all multiplied by g prime of x dx. Okay, now this is quite the very interesting problem here because we have all of this confusing business here inside of a definite integral. Okay, but if only it wasn't so confusing to begin with. Of course, when you take a look at this, we need to draw a connection for those of us who are a lot more experienced with this type of differentiation, right? As you can see, right, we have g of x listed inside there, but then multiplied by g prime of x on the outside, right? And then, of course, the original f prime of x is waiting there on the outer layer of that, right? Of course, if we have no idea what that is, right, again, we need to draw this connection here because we have, right, think of it like this, right? What if instead we ran it, right? Because this is obviously some form of f of g of x listed inside there, but then how then would it go then from what was inside of the integral as like this, right? We take a derivative of f on the outside, and then g prime of x is also waiting there on the outside. Of course, this is only done with a derivative, and of course is done by chain rule. Right? This being, right, the result of deriving f of g of x into f prime of g of x multiplied by g prime of x. Now, thankfully, because this is already listed here as an integral, this just means that, thankfully to fundamental theorem of calculus, this will just mean that we are going backwards by one step. So again, instead of going forwards derivative-wise, we are integrating backwards, right, from the result of the chain rule back to the original equation that we had. So that's going to be f of g of x, right, as a result of this integration, then going from -2 to +3. Right? Again, we have to draw that from the result of a chain rule to give us what was inside of the integral, and then by running it backwards to one step will then leave us with exactly that. So let's go ahead and solve for this integral by plugging in the limits. So f of g of 3 minus f of g of -2. Okay? So g of 3 and g of -2 are the first steps to solving this kind of problem. Right? G of 3 listed up here, so g of x and 3 being +1, and then at -2, so g of -2 is -1. Okay? So keeping track of all that, so that's going to be f of +1 for g of 3 minus f of g of -2 being -1. Okay, then going f of 1 there in the table, again, just going to refer back to that. So f of 1 is going to be a +2 subtracted by f of -1, which is a +8. Okay, then we end up with -6 at the end of this integration. Okay, so this just took a few extra steps for us. Again, making sure we do that connection properly of what the chain rule will look like if we did integrate it, running it one step backwards from what was requested, and that will conclude it for problem number 5. Okay, so problem number 6 actually, so I'm going to copy down the problem, but because it is a slope field problem, as we conclude this bit here, we will have to do one problem on the packet, but we'll move to that when we get there. So problem number 6 begins that we want to consider the differential equation dy over dx being equal to all of 3 minus y times the cosine of x. Okay. Then it tells us to let, in this case, y be equal to f of x. Okay, be the particular solution. Solution to the differential equation. with the initial condition, f of 0 being equal to 1. Okay, and so we have it listed out just like that. Okay, now for part A, this will be done on the packet. Okay, the reason why, of course, is because part A is asking for a slope field question. Okay, and we have this right here listed out on part A. We have all these little tick marks of the slope field coming across for all the values of x and y listed out there, and they want us to sketch a possible solution curve going through the point 0, 1, as is shown, right? 0, 1 is going to be this point right there. Yep. So because of this, right, I won't be copying on all these tick marks. That's way too much. All we need to do is list it out right here, and then we'll refer back to it when we start correcting. Okay, so with a particular solution that could go through following all these curved lines, again, we can go on either side of this 0, 1 point, and we just need to follow the slope fields as they're going. So again, we are going upwards, so we're calling up, and then we go to a 0 tangent line, right there, between 1 and 2, making sure we keep it exactly flat at the end of that, and then we start decreasing after the fact like this. Okay, and then going on the left side is going to be very similar. We're decreasing, but we hit a 0 slope coming across here, okay, in between -1 and -2, and then we start increasing after the fact like that. Okay, so this is indeed one possible solution curve. They're not exactly going to be very big sticklers on every little detail on this type of particular solution curve, but nonetheless, though, it needs to be at least close enough to what they were looking for to make sure that you're following all the guidelines for the slope field as you move across this. Again, making sure to know where you're increasing, where your 0 slopes are, and then where you're decreasing as you follow along those lines. Okay. So with that, that's all that really is for part A. It really is just a 1-point problem right there. So let's go over to part B, where then it will tell us to write an equation for the line tangent to the solution curve. Solution curve in part A at the point 0, 1, okay, and then use that to approximate f of 0.2. All right, very nice. Okay, so once again, we're doing a line tangent, right, at the exact point 0, 1, and then we need to do an approximation after the fact. Okay, so a tangent line equation, of course, means that we need to set up the equation as y is equal to m multiplied by x minus h plus k on the outside. Again, this is going to be the tangent line equation. Tangent line equation that is going to be called for here. And with the point 0, 1 already being listed, that's going to be h, k in that order as our way to find that those 2 points right there. But of course, what we're missing then is going to be m. M, of course, is going to be the slope. In this case, is going to be dy over dx from the differential equation at the start of the problem. And of course, we're going to be evaluating that x is equal to 0 and y is equal to +1. Okay, so with that, we just need to plug that directly into our differential equation setup right there, meaning that we go 3 minus 1, plugging in for the y, and cosine of 0, plugging in for the x right there. Okay. So with that, we end up with the 2 cosine of 0, thanks to our lovely memorization of some very simple trig functions. It gives a +1, making the slope equal to +2. So with that, all we need to do is plug everything in here with the m of +2, x minus h of 0, plus k of +1. All right, everything is plugged in nicely. We do get this very easy equation here. If you want to clean it up, it's just going to be 2x plus 1. Okay, but then of course we need to do an approximation from that tangent line equation at f of 0.2. Okay, so because we're approximating, we can just then easily plug in, given that we're going off of this line instead of the differential equation. We're going to go and plug in for 0.2 on the x plus 1, giving us 1.4 as a result right there. Okay, again, that's going to be f of 0.2, which is what they wanted for us to then approximate, showing approximation lines as a result of our work right there. Okay, Very nice for part B. Then let's go to part C, which of course, as we anticipated, is going to be a great big integration problem to finish this off. So we want to find that y is equal to f of x, right? The particular solution. Solution with initial condition, the f of 0 being equal to 1, right? Again, that point again is going to come up for us again, is that again at 0, 1, that's going to be the point in which we can use to then solve for this guy. Okay? Given that we need to go back to y is equal to f of x once more, all we have right now is dy over dx, that implicit differentiation for the differential equation of 3 minus y multiplied by the cosine of x, right? This needs to be taken back into the y is equal to f of x form, right? So because of that, we need to do good old separation of variables. Because if we are looking to integrate this back into x and y form, all the x need to go over to one side, while all the y's then need to go back over on the other side. Okay? So by separating this out, again, we need to do some division. So dy divided by 3 minus y to move it over to the left side, and then multiplying dx makes it match on the right side, that is. Okay? So because of that, it looks like that is going to be the way that we can get this started, and then we can run the integrals on both sides, making sure that they are indefinite integrals because there are no limits for us to evaluate at this time. Then by doing that, we can go on this side. This can be the natural log of 3 minus y. Again, integrating the fraction like that, keeping in fact that we have a negative coefficient there to cancel out with that negative y if we ever move back into the derivative form, being equal to cosine then being a positive sign as a result of integration, and of course the plus c, making sure to list that out because that is something that they're going to hound you on about because this is an indefinite integral and there is no limits, so there must be a plus c as a result here. Okay, then we must solve for c. Right, given that we have the initial point 0, 1 for the coordinates for this type of line, this function here. So because of that, we get the negative natural log of 3 minus 1, plugging that in, sine of 0 plus c. Okay. Thankfully, sine of 0, we can get that one out of the way. It's going to be 0. So with that, c can be easily isolated as a negative natural log of positive 2. All right, very nice going through that. So we can go ahead and plug that back in. So we're going to keep this going on this extra space back here. So negative natural log of 3 minus y being equal to sine of x minus the natural log of 2. Okay. So that in itself is listed out properly right there. Then from there, we need to isolate for y because that is our target, to make sure y is isolated on one side of the equation. So with that, we can first move over the negative coefficient on either side, making it positive natural log 3 minus y of the natural being equal to the natural log of 2 being positive, subtracted by the sine of x. Yep. Just list it out like that. Then if we want to remove the natural log on that side, we must take everything to the power of e on both sides of the equation. That way we can cancel out with the natural log. But then with that, we end up with 3 minus y waiting for us on the left side with a positive 2 multiplied by e raised to the negative sine of x, because that did not cancel out for that part of the equation. Okay. Then putting this through towards the very end here is that we have our last moments where we can subtract the 3. So it's negative y is equal to 2e raised to negative sine of x minus 3 on the outside. Then we just need to divide everything by a negative 1, in which we can finally have y isolated as a positive 3 minus 2 times e raised to the negative sine of x, waiting for us right there. All right, it took a fair few steps, right? This is just the way that the lines of work need to be in order for us to isolate for one variable after doing the separation of variables to run into integration on both sides of the equation. Of course, making sure that plus c was going to be in there as the result of indefinite integration. Okay, and that will do it. That is the end of part C and the end of question number 6. So with that, we can go back to our answer key here so we can begin correcting, and let's see just how well we've done overall. Okay, so here's part 5 here, and let's get to the corrections on this part. Okay, so moving down here at question number 5, right, we have that big table, which took a few minutes for us to copy out, but is all right there. Okay, then going on with part A to find the x-coordinate of the relative minimums of f from -2 to +3, right? So because of that, we just need to go ahead and make sure that we were on the same page here, right? Where x is equal to 1 is the only possible point, right? As we listed out with our number line analysis of the first derivative of f, that's how you can then describe where the minimums are going to be, right? And again, because we're changing from negative to positive, as was shown in our number line analysis, is that indeed at x is equal to 1, that's where we have that relative minimum. Okay, so that was already all shown there, so that's 1 out of 1 correct for part A. Very simple one pointer right there. Then for part B, it tells us that because, right, part B, they wanted to explain why there must be C such that f double prime of C is equal to 0 on the interval from -1 to +1. Okay? So we showed a little bit in this diagram down here about what that will look like because we had both +1 and -1 as a result of 0, right? Both having the same y value, and what that means for a continuous and differentiable function. But because we're pulling out here, they like to use mean value theorem, if I remember that last time, right? The test graders like to use mean value theorem. Again, mean value theorem in our case is a little bit more broader. Rolle's theorem is much more in line exactly with the scenario that we have both the same value for both endpoints of that limit. So f of -1 and the f prime of +1, right? Because we're comparing it to the second derivative, we take back a step to the first derivative there because they were both equal to 0, and because we were dealing with that continuous function and the differentiable function, that we have confirmed that that was going to be the case. Again, the little diagram was a little bit of an example to show that that was going to be the case, to make sure that we were going to be, right, all negative going back to positive. We must have at least one horizontal tangent, making that second derivative equal to 0 in comparison. Okay, so because of that, our work there is still going to be correct with our explanation. Again, we do mention mean value theorem as just the larger set containing Rolle's theorem, but nonetheless though, that is going to be correct on both ends because we did show that they're both equal to 0, and again, Rolle's theorem is going to be an expansion of mean value theorem for this specific scenario. Okay, then going over to part C, we just had to find the h prime of 3, meaning that we have to run chain rule properly as seen right there, right? So because chain rule again does show this properly with our line of work right there, okay, then we have indeed run everything through to make sure that by plugging in for 3 and using the table, we get 1/14. That's exactly what they want, right? Apparently it's 2 points to make sure that we run the first derivative of h correct using chain rule, and then lastly the answer 1/14 will give us 3 out of 3 correct for part C. Okay, and then concluding here with part D is that by running this, right, again, they wanted you to make sure you understood fundamental theorem of calculus after making sure that this inside the integral was a result of deriving f of g of x because of chain rule, again dictating that at the start of the problem, right? So because we drew that relationship, that f of g of x by taking its derivative will give us exactly what was inside of the integral, the f prime of g of x multiplied by g prime of x, right? All that matched up exactly 100%. So we know that f of g of x was the correct result of the integration. Running everything through will then give us a -6 as the result, as what they were looking for right there. So because of that, that is all 3 out of 3 correct for us on this last part of question number 5. Okay, so very good. That is all 9 out of 9 correct, right, for this part right here. So we can list that down here as 9 out of 9. I am running out of ink on this pen. I need to refill it next time that we're live. So I'm going to change to a different color for a little bit as we grade question number 6 here. Very good. So going to question number 6, we have, of course, that differential equation, and we had that section right there where we're dealing with that slope field. So let's change to that really quickly. Okay, all right. The solution curve, again, they show it one way because of the way that they do the tick marks. In any case, though, we have to show the 0 tangents. I think that's one that they're going to look for specifically, right? Making sure that you have those peaks right there where you need to on part of that solution curve. So with that, again, it's not going to be they're going to be quite lenient to make sure that we're just going to be making sure that we have those 0 tangents and the proper increasing and decreasing sections based off of these slope tick marks all thrown out there on part A. Okay, So with that, that is 1 out of 1 correct for part A. Then going over to part B, they want to do that tangent line. Again, meaning we have to run the differential equation to find, right, that slope of 2, which is exactly what we had back there, right, at the slope of being 2, but after plugging in 1 comma 0 into the differential equation, then setting up the equation of the 2x plus 1 as a result of plugging everything in there, we then get indeed that 1.4 as the proper approximation of f of 0.2. Right? So the tangent line equation was one thing they want to make sure we had, and of course the answer being both parts. So that is 2 out of 2 correct for part B. All right. Then finishing up right here at part C, again, this is the big problem with the trying to separate out for y. Okay, so if you want to go from top down here, is that by starting first with the differential equation of dy over dx being equal to 3 minus y all multiplied by the cosine of x. Again, we have to get that first set up with setting up both separation of variables as such to do the integration as done exactly on that step, right? Then by running the natural log of 3 minus y as shown right there, right? And then sine of x plus c, again, that's all needed, right? This exact thing, the plus c on the right side there. Then solving for c, getting us negative natural log of 2 was exactly what they wanted to see. Then plugging that back into the full size of negative natural log of 3 minus y equals to sine of x minus the natural log of 2. And then by plugging everything lastly in here, right, making sure that we raise everything to the e power right there. So we end up finally with some last lines of work, ending at 3 minus 2 times e raised to the sine of x. That is exactly going to be correct for what they wanted to see right there, right, in the exact form. So with that, right, we did, of course, by going down to tick marks here, we did separation of variables to make sure they're both on either side, running the actual integration, right, for this, right, running for the constant and solving for the constant of c. Okay, and then let's see here, we have the use of the initial condition. So again, by plugging back in there, right, to get that c. Then lastly, for solving for y, everything does match up exactly where they need to, giving us 6 out of 6 for this part. Very nice. Of course, to note is that we need to make sure that the plus c is done there. They'll dock off a bunch of points, right? They'll give you a maximum of only 3 points. They'll subtract really 3 outright if you did not have that plus c there, nor you'll get 0 points if you didn't do this part of separating our variables to make sure all the y's are on one side and the x's are all on the other. Okay, we have a viewer, Clash Slayer, saying that congratulations, saying that we're doing great. He says that he's into the 11th grade and will start doing calculus in the year after. Yes, of course. All these streams are directly recorded onto the YouTube channel. So again, thank you for coming in and letting us know about what you're dealing with right now. But we'll definitely be up here and I'll record it for you for any future viewing. Again, we have the full spectrum of plenty of other exams that we've gone over as well. So with that, we definitely would like to see, again, more viewers coming in and letting us know what they're currently dealing with at this time. But nonetheless, though, that does conclude it for question number 6. And with all of that correct, that is going to be another 9 out of 9. Okay. So, thankfully, though, we have ourselves here, our total amounts listed out here. Again, unfortunately, we got one little miss here at question number 3. So with that, everything else was indeed correct, going down all 6 problems. So that gives it a total 53 out of 54. A whole lot better than we did last time, right? Okay. I think that deserves a little smiley in our sense here because, right, for those who have been watching a bit longer, I do have our old exam. So again, this is what we did last month. We scored only 43 out of 54 on the 2014 free response exam, right? The same packet, right? After taking about a month to go over other exams, we finally improved our grade to 53 out of 54. Again, we've lessened our silly mistakes by quite a bit, and all of the steps were written out and followed through accordingly. Okay, but I do believe that will just about do it for today. Again, any sort of other questions can be sent directly to that email or sent on that left side right there, the labcoatmath@gmail.com, right? Or again, if by letting us know through the live stream chat about what our other viewers are going through, we'll definitely try to see how we can help out accordingly. But thankfully, this is a good revisit back to test packet that gave us some problems last month, but since we're keeping ourselves very diligent with our problems here, as we're nearing the AP exam coming within the next couple of weeks, we shall definitely see what we will come back to next this upcoming Thursday as another packet awaits us. So with that, I think that will do it for today. Again, thank you all for coming in here. Again, those who put something in the chat to let us know what you're currently seeing or what you think about the stream. And we'll definitely be back once again on Thursday, 4 p.m. Pacific, to get over another set of problems. So with that, that'll do it for today, and we'll see you on Thursday.